All right, so the last part of Chapter 5, again, we're talking about flow rate and capacity analysis, and we're going to get to kind of at the end of the chapter, we're going to get to the meat of the things that you need to be thinking about as you're looking at your project. Okay, so the first thing that we're going to talk about is this throughput profit multiplier. And basically, I'm going to just kind of go to the textbook and read a little bit out of the textbook about that. But what we're saying is that small changes in throughput can translate into large changes in profits, and that's because you have fixed expenses, especially in a process that has a larger proportion of fixed expenses. You know, if you're running more units across it, you're not adding that much variable cost, and you're spreading your fixed costs across more units. And so that magnification is what we call the throughput profit multiplier. Okay, and so if I were going to go, and I am just going to read from the text here. And basically, 5.5, page 110, says, so now let us examine some of the levers available for managing the throughput of a given process. As mentioned earlier, such levers have a powerful impact on profitability. Since a large fraction of the costs of operating a process are fixed, small changes in throughput could be translated into large changes in profits. We call this magnification the throughput profit multiplier. So, and that throughput profit multiplier, we calculate it by taking the percent change in profit and dividing it by the percent change in throughput. Okay, and they give us an example that we can look at, example 5.7, and it says, so consider a process with the following economics of operation. Okay, and the fixed costs of owning and operating the resources amount to $180,000 per month. Okay, the revenue is $22 per unit, and the variable costs amount to $2 per unit. Thus, the contribution margin, right, is $20 per unit. So again, one of the things you should be kind of make a note for when you do your homework, your contribution margin is your revenues minus your variable costs. Okay, so the process throughput was 10,000 units, and so therefore the profit for July was $20 times 10,000 units minus $180,000 in fixed costs. That gives you $20,000 in profit. Okay, but now let's say that a process improvement team was able to increase the output by 1%. Okay, so we're going to recalculate those profits. Right now it becomes $20 per unit times 10,100 units, because that's only increasing it by 100 units, minus the $180,000 in fixed costs. You have a $22,000 profit. So you can see a 1% increase in throughput has resulted in a 10% increase in profits. Right, and so again, that's why they get after that throughput profit multiplier. Okay. And there's another way to calculate it, right? We could do it like what we just did, or we can say we're going to take that contribution margin per unit and divide it by the profit per unit. So for example, for 5.7, the margin per unit is $20 and the profit per unit is $20,000 per month. Okay, divided by 10,000 units per month is $2 per unit. Using example 5.5, we get a throughput profit multiplier yielding a factor of 20 divided by 2, or 10. So if the throughput profit multiplier is large, the financial impact, right, of increasing throughput is significant. And so then we go on from here to say, okay, if that's the case, what's the most effective way to increase throughput? All right. So when we talk about that, come on, you can do it. There we go. So we need to understand what the relationship between throughput capacity and theoretical capacity is. Okay? So in your own words, this is your chance to contribute today. So in your own words, when we say throughput and we say capacity, what is it that, tell me in your own words what we're talking about. What's the difference between?
Capacity is like the maximum you could have through the system, and throughput would be like what you actually put through the system?
That's exactly right. So throughput is going to be what you're actually doing, and capacity is what you say that you're able to do in the current environment. What about theoretical capacity? What is that then in comparison to capacity?
I would say what you think you're capable of producing.
Okay, so you're on the right track. It's what you think you're capable of producing, Zach?
I would say, like, in a perfect world, everything went correct. That's what you want your capacity to be.
Okay, so it's in a perfect world, and basically that theoretical capacity, if I can just restate what you're saying, it's saying that we're pulling all of the waste out of the process, and we're just doing exactly those things that we can do, right? And so what you should recognize from that is that your throughput is always going to be less than your capacity, and your capacity is always going to be less than your theoretical capacity. But you can use these measures to identify where you might be best in terms of spending your time, right, in trying to work on the process. So when your throughput, or in Hunter's terms, your actual output, is significantly less than capacity, we would say the bottleneck is external. Basically, you need more business, right? You don't have enough business to keep it busy, okay? When the throughput is about equal to capacity, we say the bottleneck is internal, and we need to increase throughput by increasing our capacity, okay? If capacity is about equal to theoretical capacity, then we're saying that our existing resources are very efficiently utilized, and extra capacity will require increasing our levels of resources, right? If they're not, though, we shouldn't say, well, we need to increase our levels of resources. We should say we need to look for waste in the system and try to remove that waste from the system. Okay, so then if the capacity is significantly lower than the theoretical capacity, then the existing resources are not being utilized efficiently, and there may be opportunity to eliminate waste. In Part C of your project, you're going to be asked to address that very thing. You're going to be asked to calculate the throughput, the capacity, and the theoretical capacity, and then using this framework, identify where you think you should look for improvements, right? Or how are you going to improve that capacity, all right? So if we want to increase the resource levels, we can do that by increasing the number of resource units. We can increase the size of our resource units. Okay. So for example, if you're working in a batch, let's say that you have an oven and it can do 10 loaves of bread, you get a larger oven, right? It can do more loaves of bread at one time. You can increase the time of operation, okay, just by adding another shift or working overtime. You can subcontract or outsource. You can speed up the rate at which activities are performed. Okay, and I have a note on that. It says often limited effectiveness and may involve investments in faster resources or incentives for workers, right? You have to have some way to promote that. Okay. And if you're trying to eliminate waste, right, you can look for, and what you should be looking for is eliminating those non-value adding activities, right? So as you're going through the processes, you're saying, what is it that we're currently doing that isn't value added, and how can we take those out? Okay. You're looking for places that you have defects, rework, and repetitions, and you're trying to take that out. Okay. What about downtime, right? One of the things that we would often see in the pellet plant, we'd have a particular type of equipment that was not reliable, and if it goes down, then the whole production line goes down. How do you make that piece of equipment more reliable? What is it that you're going to do to improve that? Okay, reduce setup loss, meaning when I transition from one type of product to another, it takes a certain amount of time to change over the equipment. I can remember when I first started at the custom plant, we had these very complex molders, right? And the changeover time from one type of door product to another type of door product was hours, right? And so what they were able to do is they were able to reduce that down to minutes as opposed to hours, okay? So again, you're looking for ways to reduce that setup loss, right? Take some of the work that's on a bottleneck to a non-bottleneck resource, right? That goes back to some of the things we've talked about earlier, right? Reduce interference waste occurs due to a lack of synchronization among resources where you have starvation or blocking, okay? So once you've resolved issues at the current bottleneck, right, you're going to have another one, right? And so you're going to shift your focus to the new bottleneck. So it's always this kind of ongoing, continuous improvement. You fix one bottleneck, you go to the next. And again, I think it's interesting, you know, at some point your bottleneck can be not enough business. And so then you have to go to your sales force and say, what is it that we can do to increase our business? So again, it's an ongoing cycle of improvement. All right, the last thing we're going to cover in Chapter 5, I'm going to cover this conceptually, and then we'll do a couple of example problems. We're going to talk about some other factors that affect capacity, meaning load batches, scheduled availability, and setups. Okay, so I'm going to go ahead. Again, I think the textbook does a pretty good job of covering what all of this is. I'll kind of scroll through the slides as I talk about the different things here. But so in this appendix, we're going to review how the equation to identify capacity needs to be modified when we're working in batches, right? In the past, we've always worked at one unit at a time. Okay, but think about if you're, again, that oven example where we have 10 loaves of bread, right, and you're doing your baking all 10 of them at the same time, it changes how the formula needs to work, all right? And I do this primarily just for informational purposes. And again, we'll take a look. You'll have probably a pretty simple problem on this on the exam, and it's for if anybody, and I don't think we have anybody here who's probably working in load batches. We'll see. We'll see. Okay, so load batches are, or often resources can process several flow units simultaneously, a phenomenon referred to as load batching. For example, consider an oven that can bake 10 loaves simultaneously. Why we say in that case that its load batch is 10. The computations of effective capacity used in 5.2 continue to apply if we just define a flow unit as one batch. So we're no longer talking about one unit, but we're talking about one batch. Naturally, the higher the load batch, the higher the capacity. Okay. The other thing we need to understand is what we mean by scheduled availability. Typically, each resource unit is scheduled for operation only a portion of the time. So example, 8 hours a day, 5 days a week, right? However, the amount of time that a resource is scheduled for operation is called scheduled availability. Scheduled availability of the resource in a process may differ. So for example, in a manufacturing setting, it's not uncommon that some areas with a plant work 1 shift per day or 8 hours and others work 2 shifts or 16 hours. Moreover, the choice of 1 day as the time period of measurement is based on the assumption that availability patterns repeat on a daily basis. However, more complicated patterns are possible. Some resource pools, for example, may be available only on Mondays and Thursdays, with the pattern repeating every week. In that case, we should measure scheduled availability in the number of hours per week. Okay? And so it's easy to modify the expression for effective capacity to account for the effects of the load batch. Okay? In order to do that, right, we're going to say that the effective capacity of a resource pool is equal to C sub I divided by T sub I times LB sub I times SA sub I. You've all got that, right? Okay? Just C sub I is a particular resource, right? And I indicates that resource. And T sub I is the flow time for that resource. And LB is the load batch for that resource. And SA is the scheduled availability for that resource. So again, the formula looks more complex than what it actually is. So in our example, we're going to consider a resource pool containing 2 ovens, each of which bakes 10 loaves of bread simultaneously. So that's the load batch. That's how many it does at once. The baking time, the unit load, is 15 minutes. Finally, assume that the oven is scheduled for operation 7.5 hours or 450 minutes per day. The effective capacity of the pool is given as, okay, so we're going to take, we have 2 ovens, right? We're going to divide it by T sub I, which is 15, times the load batch of 10, times the scheduled availability, which is 450, says that we can do 600 loaves per day. Okay? And again, that verbally is all described on page 117 of your text. Okay? All right. So that's the load batch part of it, but now we also have to consider setups and changeovers, right? Because they impact how much we can actually get done. So consider now the effect of setups. In a process that involves multiple products, it may be necessary to set up the process each time the product is changed. So the cleaning, resetting, or retooling of equipment in order for it to process different product is called the setup or changeover time. For instance, the painting robots in a paint shop require draining the pipelines and cleaning up the painting heads each time the color is changed. Similarly, when researchers in a research and development organization switch among several research projects, they are likely to waste time with every such switch. We denote the average time required to set up a resource at a resource pool sub I for a particular product by S sub I, which just means the minutes per setup. Okay? So assume that once the setup is completed, we run a continuous batch of Q units, okay, of the same product before we change over and set up the resource unit for the next product. We refer to Q as the setup batch or lot size, okay? And you're going to need to keep setup batch and lot size different than load batch because they're 2 different things, okay? And we'll talk about that a little bit more here. Since we utilize one setup for Q, right? So what means, so the average time for setup per unit is S sub I divided by Q sub I. So it's taking our setup and dividing it by the number of units that we're going to run across it. This time should be added to the unit load of the product to yield the total unit load because it's a component of how much we're going to be able to produce. Okay, so And just so again, note that Q is different than the load batch. Q represents how many units will be sequentially run through the process after a setup has been done. Okay, load batch represents how many units can be done within each load. So for example, let's go back to our bread baking oven. Maybe I have to set the temperature at 350 and it takes 5 minutes for the oven temperature to reset. Okay, while my load batch is that I'm going to do 10 units at a time, maybe I'm going to do 10 batches, so my setup batch size is going to be 100 because I'm going to run 100 through based on that one setup, right? But my load batch is only going to be 10 loaves at a time. Are you seeing the difference between those two? So you can set up and you can run multiple batches across it, right? And so your batch size is how many you can do at one time, and your setup size is how many of those units are you going to do before you change the setup, and they're not one and the same typically. Okay, all right. So when I look at total unit load, I'm saying that my flow time plus my setup time divided by the number of units I'm going to run, right, is going to give me total unit load. Okay. And then my effective capacity then has to be revised to say it's going to be the number of resource units divided by that total unit load. Okay? All right, so let's look at a couple of examples. For example, assume that the unit load of a given product, T sub I, is 10 minutes per unit, and the setup time is 60 minutes per batch. Okay? So in Table 5.9, and I recreated it in our PowerPoint here, we summarize for various sizes of batches the total unit load and the effect on capacity. Okay, so what you're going to do is if Q is how many units we're going to run across it, right, then we're going to say that the time of the total unit load is going to be the 10 minutes per unit plus the setup time divided by 5 units, right, because I'm spreading that setup time across those 5 units. And that gives me 22 minutes. Okay, so my capacity per minute is 1 every 22, right? And my capacity in units per hour is 2.7 units per hour, and that's just using algebra to convert to hours, units per hour as opposed to units per minute. If we look at, let's increase that batch size to 10, right? Now I'm taking that 60-minute setup time and dividing it across my 10 units, right? So now my total unit load is 16 minutes per unit. Capacity per minute, the inverse of that, 1 unit every 16 minutes, or 3.75 units per hour. And so basically while we're showing mathematically here is that as I increase the setup size of how many units I'm going to run across the setup, right, that then decreases my total unit load because I'm spreading that setup size across more units.
So is it 10 minutes the setup time, or is it 60 minutes the setup time?
60 minutes is the setup time.
Okay, and then the 10 minutes is how long it takes, like the actual process?
Exactly.
Okay.
Exactly. Okay. So what is the right lot size or the size of the setup batch? On the one hand, the higher we set the lot size, right, the lower the total unit load will be, and thus the higher the capacity. So you might say, well, that's it. But then you have on the other hand, right, the higher we set the lot size, the higher the inventory will be, and then consequently, using Little's Law, the higher the flow time will be. So we explore that relationship. They talk about that in Chapter 6. But what I want for you to know is just that there's a balance, right? Setting up and running 1,000 units in this example, and then you're going to have, 890 units of inventory, right? Or whatever that might be. So you have to find a way to balance that, and that's what you do in the real world. Is you say, well, in lean environments, you typically try to reduce your setup time so that you can change over and go faster. I mean, that's where the focus is in terms of lean environments. All right. So I just want to make sure you understood that relationship between how we would account for if we were doing things in batches. Okay. All right. That being said, we're going to finish up today just looking at the last couple of problems in Chapter 5. And I think we had worked all the way through 5.5, and so we just need to look at 5.6 and 5.7 today. Okay, and so the problem for 5.6, so a company's average costs and revenues for a typical month are 15 million and 18 million respectively. Okay, so we know that our total cost is 15 million and our total revenue is 18 million. Okay, and then it says it is estimated that 33% of the costs are variable. Okay, so if I want to know what my variable costs are, okay, I can either take 15 times 0.333 or know that a third of 15 is 5, right? So my variable costs are 5 million. Okay, and the rest are fixed. So I've got variable cost at 5 and I've got fixed cost at 10. Okay. All right, and then it says, so what is the throughput profit multiplier? And I'll go ahead and increase this a little bit because I don't think we're going to need all the space, right? I'll just copy over from the text. Our throughput profit multiplier equation says we want to take our contribution margin per unit divided by our profit per unit. Okay, so and in this case, we don't have per unit, we just have monthly costs, but we're talking in the same unit of measure, right? Everything is considered monthly. So I can take my contribution margin per month divided by my profit per month and still get there, right? So help me out with what's my contribution margin per month? What did we say our contribution margin was? How do we calculate it?
Revenue minus variable costs.
Revenue minus variable costs, right? That's our contribution margin. So our contribution margin for the month is going to be 13 million. What's our profit for the month going to be?
Revenue minus all costs.
There you go. Total revenue minus all costs. Okay? All right? And so that being the case, then I can figure my throughput profit multiplier, which is going to say that it's going to be my contribution margin per unit, and in this case it's per month, right, divided by my profit per month. Okay? So my throughput profit multiplier is 4.333. So basically what that's saying is that for every 1% increase in my throughput, I'm going to get a 4% increase in my profit. Okay, so that's going to be that relationship. That's going to help you understand that relationship. And that's why, again, when you've got fixed costs, right, that increasing the throughput makes such a difference because you're spreading those fixed costs across a wider array. Okay, everybody tracking with how we did that? The keys there are making sure that you understand when we say contribution margin, you're taking your revenue minus your variable costs. And when you say profit, that one should be a no-brainer, right? The profit is your total revenue minus your total cost. Okay? All right. So then let's take a look at 5.7. Again, a relatively easy problem. Basically, it says re-examine exercise 5.1 and assume that the capacity waste factors of the paralegals, tax lawyers, and senior partners are 20%, 30%, and 35% respectively. And so then what is the theoretical process, the theoretical capacity of the process? Okay, so basically if we go back to 5.1, we had our effective capacity of a resource pool. Our paralegals were able to do 4.8 contracts per day. Our tax lawyers were able to do 12 contracts per day. And our senior partners were able to do 8. So if I say that my capacity waste factor is 20%, 30%, right? And for my senior partners, it's 35%, right? In order to calculate the theoretical capacity of the resource pool, the formula is you take your effective capacity and you divide it by 1 minus your waste factor. Okay? And so therefore, my theoretical capacity says that I can do 6 contracts per day for a paralegal, 17 for a tax lawyer, and 12.3 for a senior partner. Okay? And again, you're going to need kind of this little piece that we did today in terms of talking about how theoretical capacity, well, let me start with throughput, capacity, and theoretical capacity, how they relate, and then how you use this waste factor. That's all going to be part of what you need to do in Part C of your project. Okay? So that should give you, you should be in good shape to go ahead and finish up your homework for Chapter 5. We'll meet again on Tuesday and do the exam review, and again on Thursday we'll have the exam. So that being said, that's what I've got for you today.